Hi everyone. So in the last video we introduced this idea of impedance. And impedance captures both the resistive and the reactive components of a circuit. Both the resistive and the reactive components create a relationship between the voltage and current in any kind of RCL circuit. And so the impedance represents the magnitude, because that's what we did. We calculated basically the resistive component, calculated the reactive component, which is the difference between the capacitive and inductive components, right? And combined them using Pythagorean's theorem, and that represents a magnitude. Well, there's also an angle associated with all that vector math, and there is a use for that angle, and it's in this power formula here. And although this power formula looks very similar to the fundamental power formula we introduced at the very beginning of DC electronics, you know, P equals IV, the symbols represent different things. This P here represents the average power consumed. The I and the V represent the RMS voltages. The RMS values for the current and the voltage. So in the previous more fundamental formula, all those values were the instantaneous values, what they were at a particular moment in time. Now, that formula actually is still true. So if I think fundamentally what's happening is that, you know, this is a general circuit. You know, so I've got a voltage and I've got a current, and they're displaced by a certain phase. You know, this is going to be dependent on the relationship between the resistor, capacitor, and inductors and how they all fit together. But once you do all that math, once you figure it out or measure it, you have a certain differential here between the phase shift, right? Now, if I calculate what the power consumed at any particular moment of the circuit, it's the combination of, you know, you draw a straight line. You multiply this value times this value, whatever it is. And that is the instantaneous power that's being consumed by the circuit. Now that power does three things. It is transformed into heat in the resistor, it feeds the electric field through the capacitor, and it feeds the magnetic field through the inductor. Now that feeding of the fields, the electric and magnetic fields, can go both directions, right? I can either increase the field or I can decrease the field and pull that power back. And so there's a fundamental difference between resistive and reactances, right? The reactance doesn't actually consume, or there's no net consumption of power. There's only an instantaneous transfer that eventually gets reabsorbed, right? It's like a loan, that the energy is loaned to the field and the field pays it back. Whereas the resistor, it just consumes stuff. There's no payback from a resistor. So it's the resistive element in the circuit that actually draws, consumes, and destroys power. But there is always a fluctuation in the instantaneous power because we're consuming, we're dropping energy through the resistor, or we're feeding or taking energy from the electric magnetic field. So the power in the circuit is oscillating also. So that's why here the power is the average power over, you know, a certain period of time. This isn't the instantaneous power. The instantaneous power is just IV. But this average power is really the power, the leftover power consumed is really from the resistive element in the circuit. And it's interesting, if you do the math and take this curve, multiply it by this curve, introduce a little bit of arbitrary shift, you get another sine wave curve, and like I said, the instantaneous power oscillates back up and down, up and down, up and down as it feeds the resistor, the electric field, and the magnetic fields. But mathematically, when you combine these two trig functions, you multiply them together, you get another sine wave curve, cosine curve, but it's shifted up a certain amount. And that shift is the resistor. And that shift here is going to be the average power, right? The average is right along this center line. And because it's shifted up a little bit, we have a net consumption of power. And like I've been saying, this is really due to the resistor. And so it's interesting that using these phasors, we capture information in both the magnitude and the direction, which gives us the impedance, or the relationship between voltage and current, and the power consumed is connected to the angle.